Okay, for my AP Bio class here, I need to get this so it doesn't look like my head is getting cut off. There we go. So I want to have a little talk about surface area and volume and how this relates to cells. And I'm going to do this with a demonstration. So I got my handy dandy balloon, you know, super expensive. So I got a set volume here. And what volume it is doesn't really matter. And it's basically a sphere, right? So if I blow into it a second time, the volume's going to roughly double. And I want you, the volume is 3D, but the shape on the outside, the surface area, that's really two dimensions. That's what you would get if you just scalped the balloon this way and laid it out flat. So notice the volume has gotten bigger, but the amount of actual tissue that this balloon would take up really hasn't changed a whole lot. I mean, it's expanded some. The surface area has increased, but it's not like it's, oh my gosh, bigger area. And let me just do that again. I hope I never get too old to enjoy that. Again, that's about half, you know, emptying my lungs once. There's the volume. Volume's doubled. The surface area definitely has not doubled. It's gone up, hasn't doubled. Okay, I won't do that. Okay, so on your AP equation sheet, you guys get this. So the surface area calculations for some common shapes are given to you. For a square, 6s squared. And remember, that's a side, because unlike a rectangle where your sides are all different lengths, it's the same measurement. So here it's 2 times the length and width plus 2 times the length and height plus 2 times the height and width. And what you're really looking with all of these is you're looking at the faces of the cube. You've got 6 faces. Oh, you've got 6 faces here. Okay. Well, with the sphere, you've got 4 times, there's our old friend pi, and the radius squared. Okay, nothing too remarkable here. Well, now let's look at things in 3D. So we're looking at a square. Well, the volume is the measurement of a side cubed. Remember, when you're taking something to a power, that's the side multiplied by itself. The side times the side times the side. Anytime you go from squared to cubed, taking something to a higher power, this really dominates. Length times width times height. Just because you're multiplying here, again, instead of adding, that becomes a really dominant factor. And especially here with the volume of a sphere, 4 pi times the radius cubed. That becomes a very dominant term. So one of these two ways, hopefully it makes sense to you, either the visual of the volume going up and the surface area not going up, or looking at these terms. Now, if that doesn't get it for you, let's look at some hard numbers. And let's do squares and spheres, because this just gets cumbersome, and let's make it easy. And not only that, let's make it even easier still. Let's look at 5s and 10s, because that makes the math simple. And when we're looking at cells, we're asked to take a look at volume to surface area ratios, okay? And that's just a way of comparing, saying, okay, as our volume goes up, what happens to this with the surface area? The surface area is the denominator, and just keep that in mind. Okay, so the cube up here is the top one. Let's just do that math first and ignore this column here until we get to the very end. So we got a 5 centimeter cube and a 10 centimeter sided cube. So if you're looking at the volume, well, 5 cubed, that's 5 times 5 times 5. That is a volume of 125 cubic centimeters. Well, just by doubling the length of the sides, that's 10 times 10 times 10. That's 10 to the third power. That's 1,000. And just looking at that, that's an 8-fold increase in volume. Now let's look what happens to the surface area when you go from 5 to 10. Well, 6 times 5 squared. Well, that's 6 times 25. That's 150. 6 times 10 squared. Well, that's 100. That's 600. Well, my volume went up a factor of 8, but my surface area went up a factor of 4. So I don't want to get the impression that the surface area doesn't go up, but it doesn't keep up with the volume, not in proportion. Let's look at the sphere. So 4 pi cubed to 4 pi squared. So pi is the term that messes it up. I can't do this math in my head. I actually have to put it in there, even though it's 3.141, blah, bitty, blah. Well, when you put that in there, that's 1571. But look at this. I mean, again, look at the factor it goes up by there. It's going to be another factor of 8. 12,566 cubic centimeters. It's incredible. Do the same thing over here. You go from 314 for a surface area to 1,257. So what happens to your ratio here when you compare them? Well, look at what happens to your volume to surface area comparison. You have a volume of 125 cubic centimeters to a surface area of 150 centimeters squared. Oh, your volume is actually lower than your surface area. But when you get over here and you double the length of your side, oh shoot, my volume has gone up considerably. Imagine what would happen if you went up by another factor of 2. This is going to go through the roof. Same thing with a sphere, which better approximates the shape of a lot of your cells. Your volume to surface area ratio doubles. So what does this mean? Well, think if you're a cell. Think if you're a small cell and you're trying to get waste out of the cell, things back in, or if you're an active cell and you're trying to mitigate heat and you're trying to get heat away so you can keep at a constant temperature and cool off, what happens if your volume goes up? The only way that you can get rid of waste and take things in that you need and dissipate heat is that if you have a surface with the environment, if you have a surface area. Oh, well, as I start increasing my volume, my surface area doesn't keep up. And it makes getting rid of things harder. It makes taking in enough things harder. It makes getting rid of heat harder. So as you get to be a more complicated organism, you've got more organelles you need to stuff in there. You've got more messages to carry out. This is a sign of higher life. But if you get too big, you might outstrip your needs. So that's just something to consider as we go forward. And what, if anything, can a cell do? Because as we're looking at this here, we're assuming that, oh, we've got a smooth exterior on our surface. Because when I did the balloon, that's smooth. So what are some possible mechanisms or some possible strategies that could potentially evolve that might then say, hey, as we get bigger, this is just a rule. It's going to happen. Can I do then anything to have a greater surface area to make this ratio more favorable so that an increase in volume isn't so hard for a cell to deal with. Keep that in your back of your mind as we're dealing with cells and membranes and organelles. Thanks, guys.